So through a use of an example, I want to show how you would model in Verilog a finite state machine. So the example I'm using is an FSM counter, where this counter counts non-sequentially. It will count 2, 0, 7, 5, 3, and then it just repeats. So the black box model of this counter looks like this. There's three inputs, as you can see: a clock input, enable input. When the enable is asserted with the 1, the counter will progress through the count, and if the enable is not asserted, if it's a 0, it's just going to stay at whatever count it's at until enable becomes a 1 again, and then it will continue through the sequence. And it has an active low asynchronous reset. And then there's two outputs. One output is the actual binary count, and the other output's an LED that will light when the sequence starts and also when the sequence finishes. So anytime you're doing any sort of FSM design, you always start with a state diagram, and you'll see that once you have the state diagram, to go and write the Verilog code to model that FSM, it's pretty cookbook. Okay, that you'll see that this Verilog code that I have in this example, it's pretty much a template for any other type of FSM design that you would do in SystemVerilog. So here's the legend of my state diagram. You always want to have a legend with any state diagram that you have. So in the legend for a state diagram, the bubble represents the state, and whatever output you put within the bubble, here I'm putting my 3-bit count that I'm labeling B0, B1, B2 inside the bubble, because that output only depends on the state that we're in. And anytime you have an output that only depends on the state, that's called a more output. Okay, so more output in your state diagram, it always goes within the bubble, since the bubble represents the state. Okay, so more output. Okay, you can also see the asynchronous active low reset is shown in my legend. And then here, this enable, this is an external input that we have. You know, on the board, this would probably just be, say, a button that when it's pushed, the counter is going to progress through its sequence, and when the button's not pushed, the counter is just going to remain at whatever count it was at. It won't progress through when the button's not pushed. This LED, this output, it not only depends on the state, but it also depends on this external input enable. So when you have an output that not only depends on the state, but also on, you know, some input, that's a mealy output. So this LED output is a mealy output. Okay, because it not only depends on the state, but it also depends on this input enable. So this is the timing diagram that describes the function of this counter. That if we're in state A, okay, our binary count output is going to be a 2, right? That 0, 1, 0, this is binary for 2. And if we're in state A and the enable is inserted, okay, enables 1, well, the LED is going to light and we're going to go to state B. but if the enable is not inserted, okay, equal to a 0, the LED is not going to light. That's what we mean by the bar over the LED, and we'll just stay in state A. Okay, if we're in state B, if we get the enable, we'll go to state C. The LED will be off, and if we don't have the enable, well, we'll just stay in state B, LED off. When we're in state C, oh, and also as you can see in state B, the binary count would be 0. Okay, in state C, our binary count is 7, and we'll go to state D if the enable is asserted. LED's off, as you can see. Enable is not inserted, we stay in state C, LED off. In state D, our more output is a 5, and we'll progress to state E if the enable is asserted. If not, if the enable is not asserted, we just stay in state D. And then you can see here in state E, our binary count is a 3, and if we have the enable, we'll progress to back to state A. So this this right here, going from state E back to state A, that's the counter repeating the sequence. And once we finish the sequence, well, the LED lights again, just like the LED lit when the sequence began. If at any point, any time we get an active low reset, well, it's going to bring us right back to state A. Okay, again, this resets an asynchronous active low. Okay, so that's the state diagram that describes the operation of this FSM counter. And now here is the Verilog, the system Verilog code that models this counter. So just like in modeling that you've been doing with system Verilog prior to this example, you have your inputs and your outputs. Okay, just like in any other Verilog design source file. But when you're doing an FSM, after where you have your inputs and outputs, you need this parameter block. You can see that under this parameter section we have the names of our states. Now I called my states A, B, C, D, E here, but you can use any labeling you want. But because I have 5 states here, we need 3 bits, right? Because with 2 bits you can only have 5, or excuse me, with 2 bits you can only have 4 possible values. So 2 bits isn't going to be enough for our parameter here, for our parameter bits, because since we have 5, we need 3 bits, since with 3 bits we can have values 0 through 7. Then after this parameter block, you need to declare next state as logic, and also present state as logic. And here I'm initializing the present state to state A. Okay, so it's important that you follow this order, that the code does have to be in this particular format. Okay, then after logic, next state, logic, present state, then comes your always FF block, and this is a rising edge triggered FSM, so that's why you see the positive edge clock here. And since the reset is asynchronous, inside the sensitivity list here for the always FF block, we need to have this negative edge RST. Remember that whatever's inside the parentheses for this always FF block, when it occurs, when the positive edge of the clock occurs, that's when this block's going to be evaluated. So this block gets evaluated on every positive edge of the clock and every negative edge of the reset. That's what makes this asynchronous. If we didn't have this negative edge reset in the parentheses and we still had it down here in the block, well, then the reset would be synchronous, because it would only be evaluated on the positive edge of the clock. Okay, by including this negative edge reset, this reset will get evaluated if it changes, right? Doesn't depend on this clock changing any longer if it's written between the parentheses here. That's what makes it asynchronous. All right, and you can see if the reset is asserted, active low, and it's equal to 0, we're going to go back. Present state's going to be state A, so we'll go back to the state here. Else, present state is going to be assigned to next state, and what determines the next state is in the always com block, which follows this always FF block. So if we go to the next page here, okay, this shows the rest of the code, where after the always FF block now comes the always com block. So at the top of the always com block, you want to initialize your outputs. So you can see I initialize my outputs here to 0. And when the present state changes, that activates this case statement. And now this is just a matter, this case statement is just a matter of translating this state diagram into the case statement. That we're going to have, in the case statement, we're going to have the coding for state A, state B, state C, state D, and state E, and then along with the default state at the very end of the case statement. So here for state A, what comes first is you put what your more output is equal to for that state. So for state A, I have a more output of binary 2, so I put that right after the begin for state A. Remember, a more output only depends on the state. So once you're in that state, whatever more output you have, or if you have more than one more output in your particular FSM, you just put what those outputs equal for that state right here. Okay, but remember the mealy output, which is LED in this example, mealy outputs not only depend on the state but also on external, here just an external input. Sometimes they depend on more than one input, but the key being that here the mealy output is conditional, right? Because depending on what the value of this input is, this enable input, whether it's a 1 or a 0, right, asserted or not inserted, that's going to determine where we go, whether we go to state B or whether we stay at state A, and it also determines what this mealy output is, the LED output. So you can see here that I'm using an if statement, that if the enable is 1, well, we go to next state is state B and the LED is lit. Otherwise, we just stay at state A and the LED is not lit. Okay, and then state B, okay, it's the same idea, that first you put the more output, which is our binary count, right here, where we're setting the count to binary 0, and now we've got another if statement that determines our mealy output, the LED, and enable again is going to determine whether we go to state C or stay at state B. All right, so the rest of this code is just translating the state diagram into our case statement. So here's state C here. Then after that, we've got state D, and then state E. And then at the end of the case statement, you do want to have a default case. Okay, I made my default case here, state A. Okay, and then you want to remember to end the case and have your ends to your always com block and also the module. So as I said at the beginning of our talk here, really the key to doing FSM design in SystemVerilog is to have your state diagram. Once you have your state diagram, it is pretty cookbook going from that state diagram into the SystemVerilog code that will model your FSM.